5 minutes. 5 is 25 minus 5. Okay, so your signal 15. Okay, good. Perfect. Good.
All right, welcome to the last in-person session of QIP 2022. And our first speaker of this session is Shyan from MIT, who's going to speak about near-optimal quantum algorithms for string problems.
Okay, thanks for the introduction and thanks for coming to my talk. I'm Shyan and this is joint work with Shyan and Akmal from MIT. So this work lies at the intersection of two different areas, combinatorial pattern matching and quantum query algorithms. In combinatorial pattern matching, we deal with a large amount of strings which arise in many applications such as bioinformatics and data mining. And there are several very basic algorithmic problems on strings that we would like to solve. Let's look at some very basic examples. In the exact pattern matching problem, we want to know whether the pattern S occurs in the text T as a substring. In the longest common substring problem, we want to find the longest string that occurs in both S and T as substrings. In the minimal string rotation problem, we want to rotate the input string to minimize its lexicographical order. And there are many other such problems. So these problems date back to the early days of computer science, and they have well-known linear time classical algorithms, such as the famous KMP algorithm and the suffix tree algorithm for solving longest common substring, and so on. And the question here is how much quantum speedup is possible for these basic string problems. So first, let me quickly describe the computational model that we are using here, which is the standard quantum black box model. We assume the input string is given to us as a quantum oracle. And by querying the oracle with index I, we can obtain the ith character in the input string. And we can perform these queries in superposition. For quantum query algorithm, we can measure its efficiency by its query complexity, which is simply the number of quantum queries made to the oracle. And under this measure, every problem can be solved trivially using n queries. But in this work, we also care about the time complexity, which additionally counts the number of elementary gates used to implement this quantum query algorithm. And our goal here is to get time-efficient implementation, which means that the time complexity is at most the query complete times polylog n. And under this quantum black box model, one of the earliest such results for string problems was given by Ramesh and Vinay in 2003, solving the exact pattern matching problem in roughly √n quantum time up to polylog vectors, which we will not care about in this work. And this is nearly optimal by a reduction from the unstructured search problem. And in this work, our results are near optimal quantum algorithms for many other string problems. So here is the table in our paper summarizing all our results. So for some of these problems listed here, we improved the previous quantum algorithms and achieved near optimal sublinear query and time complexity up to subpolynomial factors. And some other problems listed here, they were previously only studied in the classical setting. And we also gave near optimal quantum algorithms in this paper. So I will not go over all our results. Instead, I will focus on our longest common substring algorithm, which is the highlight of this work. So let me first recall the problem definition of LCS. We are given two input strings S and T of length n, and we want to output the maximum length D of a common substring that occurs in both S and T. And here is an example where the LCS has length 4. And this should not be confused with a different problem, the longest common subsequence problem, which shares the same acronym LCS. In our LCS problem, we stress that the substring is a contiguous fragment of the input string. The previous work by Legal and Seligin showed a quantum algorithm solving the LCS problem in roughly n to the 5/6 query and time complexity. And they also showed n to the 2/3 quantum query lower bound. In this work, we showed a quantum query algorithm that matches this n to the 2/3 bound, and it is time efficient. So this closes the gap left open by the previous work of Legal and Seligin. So before describing our improved LCS algorithm, let me first review some of the observations from the previous works. So let's first look at a closely related problem, which is the bipartite version of element distinctness, where we are given two lists of integers S and T of length n, and we want to decide whether these two lists have a common element. So this is equivalent to asking whether the LCS between S and T is 0 or at least 1. So this can be seen as a easier version of the LCS problem. And for this problem, its quantum query complexity is well understood due to the following two famous results. Aronson and Shi showed that this problem requires the quantum query lower bound of n to the 2/3, and Unbindings showed a quantum walk algorithm in n to the 2/3 query matching this bound. And this quantum walk algorithm can be implemented time efficiently if we assume quantum random access quantum memory, and we'll also assume this quantum memory in our results. Now let's turn to another easy problem, which is the longest common prefix problem. We are given two strings S and T, and we want to report the length of their longest common prefix, or LCP for short. So in this example, their LCP equals 3. So this is a very useful primitive in string algorithms because once we know the LCP between S and T, we can immediately compare their lexicographical order by just looking at the next position. And this LCP problem has a very simple quantum algorithm. We simply do a binary search over the prefix length k, and we use Grover search to test whether their length k prefixes are equal or different. And this whole procedure takes roughly root n quantum time complexity. Now we are ready to describe a warm-up algorithm for LCS given by the previous work of Legal and Seligin. So we first do a binary search over the LCS length. So now we are looking at the decision problem with a threshold D. We want to know whether the strings S and T have a common substring of length D. And this can be rephrased as a bipartite element distinctness problem, except that here, each element is no longer a single character. Instead, it is a length D substring in the input strings, indexed by their starting positions. And we have seen that to compare two elements, it takes roughly root D quantum time. So we can use the comparison-based version of Unbindings algorithm to solve this instance, and we can tell whether these two lists of length D substrings have a common element. And the time complexity would be n to the 2/3 times the comparison cost, which is root D. So this complexity becomes pretty bad if the threshold D is large. And to improve this, the intuition is that when the threshold D is large, then the nearby length D substrings would heavily overlap with each other. And we want to somehow exploit this fact so that in our algorithm, we do not actually need to consider all the n many possible starting positions of the common substring. So to implement this intuition, we're going to use a classical technique called anchoring. The idea is we carefully construct two sets of anchors, m sub s and m sub t. The anchors are simply positions in the input strings s and t. And in this example, they are denoted using orange circles. And these anchors could depend on the content of the input and also on the parameter d. And the requirement we want to satisfy here is that if the LCS is at least d, then there must exist an anchored length d common substring between s and t. So what does it mean? It means that if we vertically align the common substring like this, then there should be a common position inside this common substring that is included in both anchor sets m sub s and m sub t. So in this example, we have a common substring of length 6, which is anchored at its fourth position. So once we have these anchor sets, then our task becomes to find a pair of anchors x and y such that together they determine a length d anchored common substring. And we call this pair of xy a witness pair. So as we can see, this anchoring requirement is easier to achieve when the threshold d is larger. So our hope is that for larger d, we want to somehow make the anchor sets have smaller size so that the requirement is still achieved. And in this way, we can make the task of detecting a witness pair easier because there are fewer anchors to consider. A nice property of this formulation is that if we fix a pair of anchors x and y, then their anchored LCS length can be determined easily as follows. We align the pair of anchors and extend to the left and to the right until we hit a mismatch between the two strings. So equivalently, if we associate each anchor x with a pair of length d substrings, namely the prefix and the reversed suffix adjacent to x, then we can express the length of the anchored LCS at x and y as the sum of two LCP values of these associated length d substrings. Okay, so using this anchoring idea, our algorithm for LCS consists of two parts. First, we want to design such anchor sets. And second, we want to have an algorithm that can find a witness pair from the anchor set. And to get good performance, we want our anchor sets to have some good parameters. First, we want the size m to be small. We want it to be much smaller than n, the length of the input string. And second, we want our anchor sets to be easy to compute. And here the notion we require is strongly explicitly t-time computable, which means that given an index k between 1 and m, we want to be able to output the kth anchor in our anchor sets in t quantum time. And given these two parameters, we can so our algorithm for detecting a witness pair runs in the following quantum time complexity root d plus t times m to the 2/3. We can compare it with the warm-up LCS algorithm, which has a similar time bound, except that here we reduce from n to the 2/3 down to m to the 2/3. And the cost is paying an extra plus t complexity. Let me state the parameters of the anchor sets that we can achieve. Where the size is n over d to the 3/4, and the computation time is roughly root d. And we plug it in. The the overall quantum time complexity would be n to the 2/3. For the rest of the talk, I will briefly describe each of these two parts in our algorithm. So the first part, designing the anchor sets. This part is achieved by combining some tools from the literature on classical string algorithms. But I would like to stress that this strongly explicit computability property is something that normally a classical algorithm would not require, but it's crucially required in our sublinear quantum query setting because we don't want to compute the entire anchor set, which would be too slow. So we would like to be able to report each of the each individual anchor efficiently. So let me briefly describe what are the ingredients in our anchor set construction. The first is something called difference cover, and the construction is very simple. It's illustrated in this diagram, where the orange circles are included in as anchors, and it is a very nice construction. It's periodic, and so it's kind of inspired by the meeting middle strategy. And it's simple exercise to verify that every pair of length d intervals can be anchored in this way. So the good thing about this construction is that it's very simple, it's input oblivious, and each individual anchor can be outputted in roughly constant time. But the downside is that the size of this construction is too large. It has size n over root d. And our second ingredient is a notion called string synchronizing sets, which was recently introduced in Stock 19. I will not describe what it is. I will just say that it implies a valid anchor set by depending on the content of the input in a sophisticated way, so that the size of the anchor set could be much smaller. It's roughly n over d size. But the downside is that doing this way, the computation time would become too slow. So our idea here is that we kind of combine these two techniques so that we can get a trade-off between the size and the computation time. So this part is mostly classical, but we also need some quantum power to deal with some technical special cases, in particular this highly periodic case where we have to use Grover search and binary search to find the boundary of periodic regions. I will not go into details. So now let me briefly explain the second part, which is finding a witness pair from the anchor sets. And unsurprisingly, our algorithm also follows this quantum walk search on Johnson graph technique. We perform quantum walk on the Johnson graph with parameter R. So the state of the walk is R subset of the anchors. And the goal is to search for an R subset that contains a witness pair. And we are allowed to associate every R subset with a data structure so that it can help us implement the steps in the quantum walk algorithm more efficiently. We need to implement the setup, update, and checking steps. Where in update step, we need to remove an anchor from the current set and insert another anchor. And in the checking step, we need to decide whether the current set of anchors contain a witness pair given this data structure information. And let me describe what goes into our data structure. So recall that each anchor X is associated with a pair of length d substrings to the left and to the right. And the witness pair condition is determined by the LCP values of these strings. So for an R subset, the data structure contains a assorted lexicographical order of all the associated strings associated to the anchors in the set, something like this. And in addition, we also remember all the LCP values between adjacent pairs in this order. And these information together, they determine the so-called compact dictionary tree between all the strings, which in turn determine the LCP values between every pair of strings. In the update step, we use T time to first compute the anchor to be inserted. This is where the T dependency comes from. And then we use binary search to find its correct lexicographical order. And this comparison calls is root D, as we saw before. And the setup time is just R insertions. In the checking step, we want to know whether the current subset contains a witness pair. So this step doesn't require any additional queries because we already have all the LCP values in our data structure. But the problem is that the time complexity would be too large if we just do a brute force enumeration of all the pairs. So to reduce the time complexity, we need to somehow add more data structures to maintain more information in a time efficient way. I will not describe everything in detail. So this is the time bound calculation, which is not too important for this talk. I will just mention how we get around a kind of technical issue in doing this time efficient implementation. So in our solution, we need a quantum walk friendly data structure for dynamic 2D orthogonal range search problem. This means that we need the data structure to be history independent and have worst case subpolynomial time complexity for operation. And at the same time, you also have this issue that the 2D points in this range search problem, they are not integers. They are actually lengthy substrings of the input string. They are compared in lexicographical order. And unfortunately, there are no known data structures that satisfy all these requirements. So our fix is that we use a kind of simple sampling procedure so that we can estimate the ranking of the coordinates in the entire universe so that we can turn the coordinates into integer coordinates. And in this way, we can use some very good data structures. And this step will fail in the worst case, but by a simple balls and beans argument, only a tiny fraction of the vertices on the Johnson graph will fail. So it's okay to do this. Okay, so this finishes our description of the algorithm. I'll just mention one simple open question. Are there any quantum speedups for other string problems? For example, these pattern matching problem with wildcards or like mismatches. And we do sublinear quantum query complexity. Okay, thank you very much.
Thank you for your nice talk. We have time for a few questions.
Thank you for the talk. So my question may be unrelated and dumb. So do you think is there any quantum advantage or is quantum algorithms can be useful for subsequent problems? So I think there are only withdrawn quantum papers about that.
Yeah, that's a good question. So in the problems that we study in this talk, we are kind of dealing with substrings, contiguous substrings. So these techniques might not be helpful in solving like subsequence type of problems. Yeah, but I would guess that for some parameterized version of these subsequent problems, for example, in the low distance regime, where there might still be a lot of contiguous matched substrings, I would guess these kind of techniques will still be helpful. But in the general case, I'm not so sure.
Yeah, thank you.
For this longest common string problem, do you get a better algorithm than n to the 2/3 when D is large?
Yeah, that's a good question. Actually, you have a slide prepared for it. So in the follow-up work, we get, so in the extreme case where D equals N, this problem is actually easy because it can be solved by a Grover search. So in the follow-up work, we get an optimal algorithm even for this parameterized version of LCS. So it's a smooth trade-off between the 2 points.
Okay. Is this work out or it's in preparation?
It's in preparation.
Okay. Thank you.
Do you think the methods you are using could be helpful for other problems besides the string problem?
I'm not sure. I don't know. I would guess the trick that we use to get around some data structure issues might be helpful, but I don't know.
Thank you. I would love to maybe discuss in private more on the data structure part.
Sure.
Thank you.
Very nice talk. Do you think your approach can be generalized to computing the LCS between k strings, like larger than 2?
Maybe, but so even for the k element distinctness problem, the query complexity is currently not well understood. So I would guess it's too early to consider this kind of generalization.
I see. Thank you.
Let's thank the speaker once again.
Thank you.